Hi, good afternoon. Thanks for tuning in. My name is Daesung Park, Senior Solutions Architect at Student Lab. Today, in this session, we'll discuss the IMDG data source sync, as well as change data capture, aggregation, and I'll lay out some use cases as well. And I'll give you an overview about IMDG quickly, as well as what CDC is all about and how we apply CDC in real use cases. So we do have a lot to cover, so let's jump right in. This IMDG technology has been around for some time, and it essentially holds fast data as opposed to big data. With IMDG, you store in-memory data such that you do need to have some data sources where you can retrieve your data into IMDG. To do so, you can take the raw data into IMDG, but normally we would take what we call operational data. We would massage the data in the form that the applications can readily consume. That's where CDC technology comes in. How do you actually get the data off of databases and synchronize that data into IMDG? So I'll lay out some strategies how to go about to do that, and also give you the architecture we have created along the way within Torrent, and also use cases. So we have a lot to cover, as I was saying earlier. I'll give you a quick overview of IMDG. I presume you do have some experience in IMDG, so I won't go into too much detail on that. I'll lay out the statement problems, basically that describes what we're trying to solve here. And I'll lay out some IMDG synchronization options that are available today, as well as in-depth the details on IMDG sync around CDC technology. And we'll also go through some definitions that we're going to need in order to implement our solution. And we'll put all the types together into one architecture, and also give you what we've done at Torrent. And I'll summarize what we've discussed and lay out some of the use cases that are being used today. So quickly, IMDG overview, as you can see from the diagram, think of it as a cloud where you have three core features that allows you to store data, allows you to compute data, and as well as provide messaging services. And this is all done in memory, so it is very fast. We call it fast data. And you can also think of it as cache and storage. It's a cloud that has as much as data you want into in memory, and be able to access data remotely from various different applications, as you can see in this diagram. And then, however, you do need to get the data out of data sources, as you can see, and there are a number of different data sources that IMDG can connect to. So within the cloud itself, you do have data nodes, to store data, and also allow you to do some computations. And the purple circles that you see are essentially data nodes. You can keep on adding more data nodes to scale out, and that's where the elasticity comes in. We also call it a data fabric. There are a lot of terms that I can throw around here, but IMDG basically allows you to store as in-memory data and be able to compute as fast as you can. The term fast data is being used quite a bit for IMDG because it gives you microsecond latency, and it is NoSQL, key value paired lookup speeds, in-memory speeds rather. And also we tend to store operational data as of the raw data. So data itself is readily available that you can consume from your applications. So there's no transformation on it whatsoever that you need to carry out. And that's where you're going to save a lot of performance and latency and so forth. It is ideal for offloading data from databases and mainframe and such, and it also gives you many data nodes that you can scattered out within the IMDG itself, so you can do some massively parallel processing as well. And it also complements big data. Typically, you store historical data in data lakes and real-time data in IMDG. And with off-heap data store that is provided by many of the IMDG products, you can actually store upwards of hundreds of terabytes of data, which rivals big data. And scattering out and scaling up is just a matter of adding more nodes and just increasing the resource sizes and such. So stakeholder problems. So in this session, what we'll be talking about is we're going to be answering two questions essentially. How do you sync IMDG with data sources being databases in our case? And how do you aggregate data, the updates that may occur in your databases into IMDG? And this has to be done in real time, along with the aggregation going on at the same time. So there are some options that are available today. The last one that you see is what we'll be focusing on. But you can see from here, you can simply get the data out of JDBC into IMDG. Or you can have some sort of status indicators that you can use to pull the data out from the database into IMDG, and as well as triggers that can push data into IMDG. And even sourcing is sort of like triggers, except that it's done outside of the database. So I'll be covering these different options in the next slides here. So the read-through option is available with IMDG products. It is an embedded solution where IMDG itself knows how to talk to the data source to get the data. If the data is missing from IMDG, what IMDG does is essentially it goes to the database and pull the data out of the database into IMDG. This is what we call cache miss. If you don't have data in IMDG, it'll put the data out into itself. However, it does have some caveats, as you can see on the right-hand side. Data can get stale quickly because if data is already in IMDG, that will be served to your microservices in this case. So you do need to expire the data by setting time to live so that the data itself can get refreshed with the new updates that may come into the data source. So there's a little bit of downside to that, but this is popular choice nonetheless. However, you do need to connect directly to the data source. So there's another caveat. If you have too many data nodes that are running within IMDG, then you have to be able to deal with that many connections to the data source as well. So this is recommended for small scale IMDG because of the connectivity issues. Triggers, on the other hand, you do have an option for the data source to actually have embedded logic that allows you to trigger whenever there are updates that occur in your database. And triggers will simply push the updates out to the message bus in this case. And you would have some sort of OR mapper listening on your message bus and bring the data into the IMDG. Obviously, you're adding a little more complexity to this type of architecture. The message bus itself has to be available. Also, you're embedding your logic into your data source, so the portability and reusability of your code becomes a bit of challenging as well. Triggers, because of embedded the issues, the portability and reusability issues, some applications tend to do their updates outside of the database, and this is what we call event sourcing. Microsoft, in this case, would push the data into the database, and at the same time, it'll push the updates out to the message bus. So you're essentially taking out the trigger logic inside the database out to your own microservices here. So this also has some downside, obviously. The message bus itself and the portability, you're coupling your microservice with your infrastructure, so there's some portability issues as well. So jump right into CDC, change data capture. It works a little differently. Now, this diagram shows pretty much the same as what you've seen in triggers and event sourcing. It does include message bus, Kafka, Pulsar, JMS, etc. So the complexity is still there. However, what this allows you to do is that it scrapes a transactional log file of your data source so that it never connects to your data source. So that means you're not putting any load on your data source. In many applications, that's what is preferred. And it'll periodically scrape the log file and create batches of data and publish those batches into the message bus. And we would have the aggregator or OR mapper essentially that listens on the changes, and then it does the aggregation accordingly. The complexity is still there, but it really gives you a nice way to segregate your the logic from the database itself and be able to share data since you're pushing your data onto the message bus. So not only IMDG can take advantage of that data, but you can also have other applications also take on that data as well. It is near real time. That's one thing that you do have to realize it, because we are publishing data on a periodic basis. So whatever that the delay is, that delay you're going to be able to tolerate from your application. And usually we're talking seconds here of delay. For more complex relationships that you may have in your changes or your database or tables, then you probably want to introduce ETL tools such as Hazelcast Jet or Spark from Apache that allows you to collect a stream of data and be able to massage data accordingly. And we'll be covering this a little bit later in different use cases where we can apply those type of technologies. So let's jump right into some definitions that we're going to have to lay out before we can explain how we can aggregate data. There are three different types of aggregation, as you can see here. Singular means you get the data as is and push that data, very same data, into the IMDG. No changes required. Static, on the other hand, you do have a static temporal window, or STW for short, in which it is guaranteed that you will receive all of data that you need in order to aggregate the data. The dynamic type, on the other hand, it has two flavors, bounded temporal window, BTW, or unbounded temporal window. Bounded means essentially, hey, it has start and end time. You know when to aggregate data. Unbounded, we really don't know. You don't know when to start. Typically you do know when it ends, but you just don't know when it starts. So we'll cover this in detail. So singular type, as you can see here in diagram, this is the easiest case. You take the data into your internal storage. Internal storage is like a buffer, except that it is sized accordingly such that you can take on large amounts of data. And typically internal storage can be resided within your IMDG, or it can be external as well. Particularly, you probably want to have it within the IMDG itself. And using that buffer, you're going to be able to collect the data that you need and do the massaging, curation, and etc. before putting that data into IMDG. And as you can see here, all we are doing is taking from three different tables, A1, B1, and C1, as they are, without doing any changes, except that transforming into objects that the IMDG expects, and put them into IMDG thereafter. Static temporal window, STW, on the other hand, this is where most applications actually, their use cases are, where you do know the start and end time. You know when data will come in. For example, you create a shopping cart. The user makes few orders, purchases few orders, then commits the shopping cart, and that shopping cart will have a number of different orders, and it's guaranteed that list of orders will be submitted into the database, and in turn, that very same data will be forwarded into the IMDG through the CDC mechanics. Now, there's slight delay, obviously, and since this is batch-oriented, or messages are asynchronously dispatched, you do need to wait a little in order to be sure that you will have the entire set of data. So for this, we call static, and typically we use time expiration to handle that scenario. And given sufficient amount of delay, which basically guarantees that you will receive all of the data that you need to aggregate data properly. Now, for bounded temporal window, this is a little different, but nonetheless, it's similar to STW. It's, in fact, is a special case of STW is special case at PTW. In this case, you do need to know when data is coming in. You do need to find the start time and end time so that you can construct your temporal window. And within that temporal window, you're going to be able to collect everything that you need to aggregate the data that you need to do. And now that means you have some logic in your aggregator that actually look for the start time and end time of given a collection of tables, in this case, 3 tables. And so beforehand, you would come up with some sort of scheme to achieve that. And this is used widely as well too, next to STW. But what's interesting this is that since it has built-in logic of determining start and end time, you can actually use the very same scheme to handle the unbounded temporal window as well. Basically, the exercise is to determine how we're going to capture the data we need within this given temporal window so that we can properly get all the data that we need to aggregate perhaps into a single object. To achieve that in unbounded temporal window, since for unbounded, you really don't know when the data is coming in. So you do need to have internal storage that is large enough so that you can start saving the data. Now, to do so, you need to basically wait till some period of time, or you do need to tag your data that gives you some timestamp, something that will tell you, hey, this is the last data out of these batches that you have received, so that you can start aggregating. So to achieve that, the internal storage itself has to be scalable. You can scale out or you can scale in based on the start and end time, or based on the window size, essentially. And don't forget, this example, what you see is just a single 3 tables with some changes, but typically you have multiple tables with very complex relationships, such that capturing rather the unbounded temporal window can be a little bit of a challenge unless you have enough internal storage where you can keep the data. So the exercise is essentially, how do you size the internal storage in a way that you can scale out as necessary. In other words, wait for the data that you need to complete your task. So you can use the very same technique as bounded temporal window, same logic, but it adds additional logic which allows you to scale your insert storage as necessary. For unbounded, unscalable, unbounded temporal window, or UTW, in this case, you don't have the start time. You don't know when it will come in. Sporadically, things will happen. Perhaps, for example, you're receiving data, but in this case, table C comes in some later time, maybe 10 or a couple hours later, perhaps, and be able to aggregate data based on that last update that you received. So storing the entire set of data for a long period of time is not feasible for most applications. So in that case, you need to do this outside of your aggregator. So you introduce what we call the external curator app, which actually reconciles data as necessary. And fortunately, situations like this do not occur that often, such that you could potentially do this at the end of the day, just go through some reconciliation. Or if you choose to, you can periodically, on an hourly basis or every 10 minutes and what have you, have an external curator to reconcile the data as necessary. And by the way, because of the curator app is running outside of the IMDG or the aggregator itself, you have a choice of using various different mediums, such as S3, Kafka, data files, and so forth, to hold your data that you need, to reconcile properly. So let's put everything together, what it means. Within Sorrent, what we've done is we spent some time trying to go through this and put all these various different types into one architecture. And here, as you can see, in this architecture, we are covering all of the aggregation types I mentioned. Here, we have data that comes into the data source. We are using Debezium, the CDC, open source that is available, freely available, and which actually uses Kafka to publish the CDC updates. And for us, it was just a matter of creating some connectors, Kafka connectors, to grab the updates from the Kafka topics and convert those updates into the objects that can be consumed into the IMDG. And those updates may come in the form of JSON or Avro objects. There are some other products I'll mention a little bit later, besides Debezium. But typically, these CDC products offer a way to register your objects through Avro, for example, such that the data itself is very compact. And also you have full-blown schema information, so you can automate the entire process of actually getting the data and turning that into something that is more suitable for your applications. And we also have a way to get the data into Hazelcast, chat, or Apache Spark in the form of stream, so that you can do some more heavy lifting in terms of stitching data into the proper objects. And also Curator, which I mentioned earlier, that can be run externally, and typically Curator does the reconciliation to overcome some stale data issues and such. So that would be the thing on the Kafka topic as well. So it covers all of the aggregation types that I mentioned. Current implementation is demoware, more or less. It supports Singular and STW, and we are in the works of having support for SUTW as well as UTW, and the query itself, of course. So This is a very nice use case that we would like to have it such way that it's generic enough, so it'll have a built-in code generator as well, so data will be automatically consumed into IMDG in full scale, fully blown rather, objects that a microservice can consume. For our implementation, what we've done is we use OpenShift. Here you can see various different containers that make up the entire architecture. We use Aggregation for registry service, where we actually push the data, Avro information rather, and that Avro information, schema information, is available to the IMDG itself, so you can actually get the information and generate the code as necessary. When I say code, we're talking about actual data classes or domain classes that we can use to stitch objects, raw data together into a single object, for example, and push that single object into the IMDG. And we have data source. In this case, we are using Postgres with a high availability built in using OpenShift. And we are able to ingest data into Postgres and be able to get all of the data, initial data, as well as updates into Division, and which in turn will push that information or data into Kafka, which is basically providing data is required by the Kafka Connect in order to stitch the objects together. And finally, we have Hazelcast IMDG down here that will basically take the data through our own connector. That is the aggregator that I mentioned earlier that does the stitching. And we have various different applications that run in the containers themselves. And these are client apps, more or less, that allow you to monitor data, browser data. You can do some troubleshooting. Also, the management center from Hazelcast, we can use that to monitor the IMDG itself. So this architecture is self-contained, so you can basically run it. We do have Ansible, a script for this. The playbook allows us to automate the entire deployment process. So it is coming to be a plug-in solution. So that's the aim for us. We want to be able to get the CDC architecture in place such way that you download, you run the playbook, and you get yourself the entire application running, that including the front end as well as the middle piece, middle tier rather, and the back end as well. So in summary, what you can see here is that we are taking data sources, in this case, Division that we are using, but we can also use Stream, Informatica, Power Exchange, Oracle Golden Gate, IBM InfoSphere, and Qlik's Tunity. These products basically allow you to capture CDC records. And those CDC records can be published in the form of typically Kafka. There are various different message buses that these products support as well as you can, if you choose, you can use their API directly. Kafka, we choose Kafka because it gives us a nice way to publish data and be able to share the data. And we also can send the retention policies on Kafka such that we can play back data, meaning that we don't need to go to the data source every time we need to import the entire set of data. Kafka itself has the data we need, or initial data we need, to populate the IMDG. And IMDG connector, which is the aggregator essentially, that has a way to pass data into IMDG. It can be passed through data curation, aggregation, and we can also do table-to-object transformation using various different techniques that I described. And also, Kafka provides fault tolerance and data replay of Kafka topics. So it's a turnkey solution in many ways, given the proper connectors. Haven't talked about initial load, but initial load is handled by the CDC product. So you can actually get the entire set of data from a given table through Kafka. But in practice, if you do have a large set of data, a large database, then that might not be feasible because reading data off of Kafka can take a very long time. So in that case, you would need to export the data out of the database in the form of files, essentially, and read that into IMDG. To achieve that, the table itself has to have some sort of timestamp, in this case, updated at column, which basically tells you when the record has been updated. And given that column, you're going to be able to control the Kafka sequence number offset such that you can import the data first from your files, then using that offset to get the updates from the Kafka topic. And as far as the importer goes, again, pass-through, data creation, filtering, and so forth. That has to be also done for initial load as well. So when do we use this CDC? If one or more of the following is true, then you may want to consider using CDC. It might be something that you might want to look into. The database is system record. IMDG is typically not the system record because it keeps data in memory. If the entire cluster goes down, then you basically lose your data. So you do want to have the system record elsewhere. And you don't want to put any more load on your database. In typical scenario, use cases where you have too many applications actually connecting to the database in the first place, and they want to be able to offload that. So you are essentially moving that data into another medium, in this case, IMDG. And you also are not allowing applications to directly access the database. But applications require data from the database. And also this near real time that I mentioned, because of that batching mechanics, you do need to be able to tolerate the near real time updates. And we're talking a few seconds, maybe depending on the settings, we're talking probably 2 to 3 seconds, maybe upwards to 5, 6, 7. If you're dealing with SAP, because SAP does a lot of updates into a number of different tables for single transaction, the delay might be a little longer. And if you want to share data, if you have many applications and you want to be able to access the very same data, it's just a simple matter of just listening on your Kafka or message bus and consume the data accordingly. And end users expect low latency. That's always the case. You don't want to click on the browser and wait for a few seconds to refresh. With IMDG, that will be instantaneous. So let's cover some use cases that we have seen, and these are the ones that I believe will benefit from CDC tremendously. So most use cases are around offloading from database or mainframe. You already have a legacy system. You want to be able to offload that data into elsewhere and access from there. You want to be able to share data. After offloading all this data, You don't want to just dedicate that for just single application. You want to be able to share that very same data to many of different applications. So there are some use cases that I'll go through here. So order management use case, this use case basically persists order details in the database. And the IMDG's job is to provide a fast order and history lookup service. It'll get the data off the database, and it'll basically give you very low latency access to the order information. And also, at the same time, it'll manage user web sessions at the same time. So if you look at the diagram of that, it flows something like this. As you can see from the bottom, system record, you have a number of different databases or tables where CDC connector retrieves the data. Again, it's scraping the transaction log, so CDC connector is not connecting directly to these databases whatsoever. It'll get the data off of the transaction log. Periodically, it'll disseminate the batches into the Kafka, which is not shown here. In turn, that very same data will be aggregated into IMDG. And IMDG will basically provide the data to the end applications, to the web server. And typically, the applications will come into the IMDG to the web server, storing some of the web sessions, providing order chart, cart information, transactions, and such. And based on that information, you can retrieve the order history and status, inventory, and etc. And typically, that access time or access latency time is very low. We're talking milliseconds. And in this case, I'm showing ERP here. This is a typical use case where you have a legacy system that's all of the writes into the system record through ERP, and yet you want to be able to access that data quickly through IMDG. For the supply chain management use case, you have more than one ERP. Supply chain is a very complex system where you have multiple ERP systems that has various different sets of data, and ERP systems themselves don't talk to each other, so data itself is not compatible. Creating the audit reports, for example, can be a very difficult thing to do, but with IMDG, you're going to be able to create those audit reports in a matter of seconds, as opposed to that may take days if you do have disparate ERP systems. For that, you can see here in this diagram, it essentially takes the data from 3 different ERP systems in this diagram, but they can be any number. And through CDC connector, you will be able to pick and choose what data that you want to put into IMDG. And don't forget, you're putting the data into IMDG in the form of operational data, fully stitched, readily consumable data, such that you no longer need to do additional transformation. The web applications will just access data. That's where key value pairs lookup service comes very handy, and that's where you are getting the performance gain. For asset management, you persist the asset details. In here, basically, you do some risk analysis. You want to do some asset allocations and manage portfolios. There's some computations that are involved in this use case. So typically, in this use case, you have your own set of data, you have some control over the database and such, and you want to be able to retrieve the data into IMDG and do some quick, real, do some allocations and risk analysis, some risk calculations. Again, IMDG can scale out with a number of different data models, so you can parallelize your computations. So that gives you power that you're going to need to do some calculations in real time. And the idea behind this use case is to bring the data in and be able to swap in and out quickly. So you'll be able to get a certain set of portfolios based on what ifs scenarios that you have created for risk analysis, and bring only that set of data and construct or do your risk calculations. Then once you're done, you just swap it out and replace it with another set of data. So that really works quite well, and that's where CDC comes in quite handy. You're going to be able to aggregate data on the fly. You can pick and choose what data that you want to put into IMDG and do some real-time computations in real time. The inventory tracking is where we do some data collection and be able to do quick searching. At the same time, we're going to be able to automate the replacing or replenishing parts. In this use case, you typically have some spare parts that you need to collect into a complete set. So there's a lot of activities that are involved for this type of application, where IMDG's performance gives you a really nice way to aggregate the data on the fly. Typically, the spare parts are scattered everywhere, and you have trucks and some parts are in transit. And some many occasions that you do need to get the data, spare parts, in a set that is usable for a given customer. And finding those spare parts scattered everywhere can be a daunting task. For this, what is simply with using IMDG, you're going to be able to get the data, get the orders, inventory, and such, and push that into IMDG through CDC mechanics again. And IMDG basically becomes a hub of spare parts, and it knows how to aggregate the data for you. So this is a really good use case for CDC. In IoT edge computing, we can also do some IoT. In here, what we do is we get the edge devices into IMDG, and we introduce another edge, the IMDG, which will collect the data. It can be in the form of IMDG or even JET, which is essentially IMDG underneath. And that can actually collect the stream data and perform some edge computations and filter data as much as it can and push that into the system record, which in turn can be read by the IMDG to the CDC connector. And this is an absolutely nice use case for many occasions where collecting large set of edge device data may not be feasible. Edge devices do publish or create lots of noise data that you may want to filter before that reaches the end applications. So that's where the IMDG part comes in nicely at the edge level. For AI, ML, for artificial intelligence and machine learning, this is where we can also excel as well. In this case, you have many different database systems where you want to be able to get the data in the form of CDC and use that as real-time updates so that you can actually not only train your model that you have created, but be able to apply the model in real time, near real time, that is. As data updates come in from CDC, you're applying your machine learning models that you have dispatched to IMDG. And you can achieve that through IMDG, or you can also have Hazelcast on the side, Hazelcast Jet and Spark, and have them to take on such tasks. It's up to you how you're going to do it. But the bottom line is that you're going to have various different applications at the front end that will be able to access the underlying mechanics. Well, I think that was kind of a quick overview. I know I went through quickly given the short period of time here. So I'll be at the chat room and one-on-one session. So I'll see you there. Thank you for tuning in.